Yeah, so far we have discussed about some important aspects of photochemistry. In the coming classes, we will be discussing more about pericyclic reactions. We will concentrate on some important reactions. Okay, so this half we will be concentrating more on pericyclic reactions. Just I will get to some nice introduction of pericyclic reactions. See, this pericyclic, early times, people thought that reactions go by a radical or it goes by ionic intermediates like cation or anionic. They were not thinking about reactions where there is no intermediates. Okay. So, they come across certain reactions which were not affected by solvent, which were not affected by pH, and after a lot of struggle they were not able to isolate any type of intermediates. So, this type of reactions they call them as non-mechanism reactions. They just call them as a non-mechanism reaction. But after Woodward, he was working on the steroid chemistries. So, he found out or he observed an important aspect. When you take steroids and if you heat it, you get a nice selective stereoisomer. But once you take the same chemistry and do it in light, he observed different isomer with selectivity in that. So, that was a very important observation seen by Woodward. So, what he did that Woodward as well as Hoffmann, you heard about Hoffmann. Okay? Hoffmann is a great theoretician and he was working on quantum. So, Woodward and Hoffmann then came together, formulated a rule called as Woodward-Hoffmann rule, which decides the stereochemistry of these reactions, and they coined them as most like a pericyclic reactions. Okay. At the same time, you heard about Foucault, right? He was also contributing a lot on this understanding about this pericyclic reactions. I think in the year 1965, Woodward and Foucault, they shared Nobel Prize in chemistry, okay, for this pericyclic reactions. Okay. The pericyclic reactions have a very good important utility in synthetic chemistry, okay, like your CC bond. You can do that. What is the famous reactions in pericyclic where you do CC bond formation? Cycle addition, your Diels-Alder reactions. Okay. You can do many important synthetic applications using Diels-Alder reactions. There were Ene reactions, you have Claisen rearrangement, Scope rearrangement. So, they started having more important in organic chemistry. Okay. So, that is a sort of introduction to pericyclic reactions. Okay. Now, we will see that how we can define these pericyclic reactions. Okay. How we can define this pericyclic reaction. Normally, I am taking a simple reaction which you have known. Okay. Take this. You can get this product, right. See, if you are not having an idea of pericyclic, let me assume that this reaction goes by sort of, if I can write that reaction goes by radical. Okay, if I assume, okay, it is not true if I assume then I can think about making the same product, right. I can call this as my intermediate, or same reaction I can assume in other way also. So, you can see I can see I can feel this reaction like this, but the interesting part of this reaction is what? This reaction is more like an intermediate reaction, it is a stepwise mechanism. Okay. If you want to write a energy profile for this reaction, how you can draw an energy profile? Basically, I have my reaction coordinate here, I have my energy. Okay. If I want to draw my energy profile, right, my reactant and my product, okay, and this is will be my intermediate. Okay. So, you say this reaction like stepwise mechanism which goes by a type of intermediate. In other hand, if I take the same reaction, say that I so I call this as a transition state, okay, because it is not an intermediate which I can isolate. So, how you can think about the energy profile? Yeah. So, it will be, if I draw my reaction coordinate with my energy, R, I have my P, and this will be my so called transition state, right. See, you have a free, so you can think about a stepwise mechanism where you have an energy profile with an intermediate in that, and you think about a reaction which goes by a like without a radical intermediate, goes to a transition state, you end up energy profile like this. So, with this, can we define now pericyclic reaction with this idea? The first thing comes in your mind is what? Your bond breaking as well as your bond making process, right. Your bond breaking and bond making happens in a concerted fashion or concerted manner, right. So, you can see the bond will be made here, same time your bond can be broken. So, both happens very concerted, okay, and it is simultaneous. That is the first thing about pericyclic reactions. The second part is that your pericyclic reaction goes through a cyclic transition state. And the third is that you will not observe no distinct intermediate can be observed. These are the three important things which you know about pericyclic reaction. So, that is how you can define pericyclic reaction. First point, you say that bond breaking and bond making happens in a concerted fashion. The second point, you show that it goes through a cyclic transition state. Finally, you say you cannot observe any distinct intermediate in this reaction. Okay, that is the very formal definition of pericyclic reactions. Okay. Now, we will see classification of pericyclic reactions. See, based on Woodward, pericyclic reactions can be broadly classified in 5 major reactions are there. Okay, 5 major and 2 are minor, which you can incorporate into pericyclic. But if you say broadly, there are 5 major classes. Okay, one is your electrocyclic reactions. Very important class where you study about your cone, rotatory and disrotatory, ring opening and ring closure. Okay, that's very important there. And then you study about your cycloaddition, and same way you study your cycloreversion reactions. Important class of your pericyclic. Another you can think about is your sigmatropic reactions. Okay. And you have your group transfer reactions. Then you have your stereotropic reactions. These are your major 5 classes which you see in pericyclic. Electrocyclic, where you study your cone and disc, right, ring opening and ring closure. Cycloaddition reactions, you study your famous 2+2, then you study your 4+2 Diels-Alder reactions. Retro Diels-Alder, where you study about cycloreversion reactions, right. Sigmatropic, you study about your 1, that is your hydrogen shift and carbon shifts, methyl shift. Then you study your Cope, Claisen, okay, all these things in sigmatropic. You have group transfer reactions, heliotropic reactions, where you study with your sulfur oxides reactions. And then the 2 other minor which you can think about, it's your ene and retroene. See, some people put this ene and retroene reaction inside your group transfer reactions, but they have a separate class, ene and retroene reactions, which you can study. Another is your co-octet reactions. So, basically that means we have to study this 7 type of reactions. Okay. So, what we will be doing is that we will be spending time on each segment of reactions, we will study in detail. Okay. We start sigmatropic, we will study in detail all the reactions involved in that, then we will move one by one and finish it off. Okay. These are the 7 reactions which we are going to see in this next coming classes. Okay. These are the classification. See, there are some methods by which you understand or you analyze pericyclic reactions by theoretically or by using orbital pictures, right. So, there are 3 methods by which you methods of three methods you use to understand pericyclic reactions. One is your study this orbital symmetry correlation method. Any idea who did this? Huh? Okay, and another Woodward and Hoffmann. Their contribution was great on orbital. Woodward and Hoffmann. Yeah, Vocals was there. Orbital symmetry. Then any other which you remember? Mobius, very good. That is totally. Another is this frontier orbital method, right? Which is very important one. Frontier orbital FMO, which use this molecular orbital theory, done by Foucault, right? This Mobius, all this comes under this theory, transition state aromaticity method. But actually this was started by any idea who did more major contribution on this? Big names. Evans, Dewar and Zimmermann. Okay. So, it is better to know the people who are contributed on this particular areas. Any chemistry if you take, you better know the people, the contributors. So, you can use these three methods like orbital symmetry correlation, FMO and your transition state aromaticity to understand your pericyclic reactions. Okay. Yeah. Before getting in detail pericyclic reaction, just I know that you guys know about all these things, but I want to just brush your molecular orbital pictures just for ethylene, butadiene and cyclo or heptatriene. Okay, just to brush it, because I know that you have studied in detail in other courses. Just have a refresh. Just see molecular orbitals of ethylene, butadiene, heptatriene. See, ethylene is, you guys have studied it, it is not heptatriene, hexatriene, sorry, hexa, right? Hexatriene. So, you know ethylene, if I say it is bonding and should be this one and it should be the HOMO, right, highest occupied molecular orbital. This should be your antibonding side and this will be your LUMO. If you see the face of ethylene, this is, you get this face, right, which you have studied, and in antibonding it will be reverse of it. You can build your butadiene based on this, right. You can call this as pi 1 and pi 2. Say, I want you guys to at least draw this. I have studied it, it's fine, but so you can take your ethylene, you can have this combination, same phase combination, okay. Then you can get this ethylene with the same phase, okay, or you can have the phase the different way, okay. Then you get the downward, right. So, you can build up from, so it is pi 1 and pi 2. Same way you can make this same way you can combine these two phases, like this is one, okay. Then you can take this phase and combine it up. One, another, this will be always, see the EC, right, your pi 3 and pi 4. Nice to slowly you can build up like this, okay. If you want to draw hexatrain, can you draw hexatrain like train system, hexatrain system, where you have like see, when we see book, we just visually we see that and we leave it, okay. When you draw it is nice. So, what you do, how you build up this system, you can take this bonding with pi 1, you end up this one, your pi 1 system. You can take this bonding and you can do with your pi 2, you end up with pi 3, right. It mix this 2, you end up pi 1, you mix this 2, you end up with pi 3, okay. That is how you build up. So, if I just, so this all will be in the same phase because of this 2 mixing, okay. If I mix pi 1 of my ethylene and pi 2 of butadiene, you just see that. Get my pi 3. Okay. The pi 2 system mostly have this type of nodes of symmetrical, which you have studied. So, this will be like 3 phases will be up and your 3 phases will be down of your pi 2, if you keep like this, okay. That is how you build your pi 2, okay. So, pi 1, pi 2, pi 3. Now, can you draw for your pi 4, pi 5, pi 6, same idea. So, now, once you know this, then it is nice. After this, you can get into your pericyclic. I know that you guys know it, but just I can say this my pi 4, okay, where you have these combinations, right? Down, I have my down, up, then I will take this one and this one, this pi 4, then I can have this combinations. This will be pi 6, okay. I will draw the pi 4, but this pi 6 will be. Okay, because this is a major you are going to talk, and your pi 6, pi 5 since I don't have space, I am drawing. That also have a type of where you have an opposite type of symmetry, same way down and up. That's your pi phi. Okay. So, you can just by combining, you can build up your systems. Okay. It does not need that you have to memorize all these things, just by combinations, how to combine and just slowly you can build up your ethylene, butadiene, triene systems, etc. I hope that you do, even for octa tetrene, you can build it up. Okay. So, that is fine about your molecular orbital. So, what we are going to learn from this, what it going to tell you? When you have a pericyclic reactions, what it tells you basically? See, when you want to analyze a pericyclic reaction, okay, first point is that you analysis of basically, okay, sorry, HOMO of one component with LUMO of another component. That is two you use whenever you see your, immediately when you see a reaction, you consider the HOMO and the LUMO, okay, and see whether. So, if HOMO and LUMO, okay, are like favored, that means their phases are same, which in detail I will tell you. The HOMO and LUMO is favored orbitally. Okay. I will explain you in detail what is favored orbitally. Then you say the pericyclic reaction proceeds. Okay. That you can understand. The third point you can understand is that the energy gap of HOMO and LUMO have influence on the rate of the reaction. Most of the time, if you see that the energy gap between your HOMO and LUMO is very small, the reaction process very fast. Okay. So, these are the three things which you can understand like by seeing your orbital. When you are given a pericyclic reaction, please see the HOMO and LUMO of both the components and see whether they are orbitally favored. If they are orbitally favored, reaction goes. If the gap is very small, then the reaction process very fast. Okay. Now, we will get. So, this is the broad introduction of your pericyclic reactions. Okay. Now, we will take individual reactions and see in detail. Since you guys have studied yes, the energy gap of your HOMO and LUMO have influence on the rate of the reaction. Okay, I know that in the undergraduates where you have studied more in detail about electrocyclic reactions. Okay, you have studied also something about your cycloadditions. I have not seen you guys study sigmatropic reactions in detail, just to have a glance. So, what I thought like I will first take sigmatropic reactions. Okay, we study in detail. Anyhow, we are going to cover Diels-Alder, cycloadditions and electrocyclic, but I thought like first I will concentrate on sigmatropic. Then we will move slowly from there. Okay. So, to start with reactions, we will start our sigmatropic reactions. So, sigmatropic reactions are broadly classified into two groups. Okay. One you call them as 1,n sigmatropic rearrangement, another you can call them as N comma M sigmatropic rearrangement. That is how you can broadly classify them. So, what is basically 1 comma N we are talking about? See, if I have a reaction, I just say this is R is a residue. Okay. Once I heat this reaction, I will number it 1, 2, 3. This 1, okay, stands for the initial position of your R. Okay. So, what happens then? You get a product like this. Okay. So, now this residue has moved across the pi system and reached a position like 3 in this case. So, that is your N. Okay. So, it can be called as then 1 comma 3 sigmatropic shift. Okay. That is how you call them 1 comma 3 sigmatropic shift. See, in this 1 comma 3, 1 is your initial, okay, where the R is, that you always number as 1, and then where it has finally moved, that you call as the N. Okay. It can be 3, 5, 7, whatever it is. See, in this R, most of the time you are going to discuss 2. Okay. One, you are going to discuss hydrogen. Okay. You call them then 1 comma 3 hydrogen shift if the R is hydrogen. Okay. Or you discuss with your carbon. These are the most you see. Either you see an hydrogen shift or you see a carbon shift, or it is methyl or whatever carbon shift. Right. These are the 2 big class of your 1N. So, sigmatropic classified as 1N and N comma M, and in 1N I can further classify them as 1 comma N hydrogen shift as well as 1 comma N carbon shift. Okay. So, what is this N comma M? So, I have a system 1, 2, 3, 1, 2, 3. Okay. So, in this case, if you see, it is your sigma bond has been moved across your pi system. Okay. So, initially your sigma bond which is doing the reaction, that you call as 1 1, okay, and where it has finally reached. Okay. In this case, it has went to 3 in one side and another side also it went to 3. Okay. Oh, double bond is there. Okay. So, this is then what system it is? Your N is 3, your M is also 3 in this case. So, you call it as 3 comma 3. Okay. There are many examples of 2 comma 3. Any example of 2 comma 3 which you know? 2 comma 3 reactions. Wagner-Maurer is 1 comma 2. Cope Claisen is 3 comma 3, 5 comma 1 comma 5. You have all your halide chemistry, sulfur halides. Okay, all your halide chemistries goes by 2 comma 3 sigmatropic shift. Okay, yeah, we will see that. So so you have to find out where the new bond is moved. Okay, in this case it is 3 and 3. So your N is 3 and M is 3. If it is 2 and 3, yes, it becomes 2 comma 3 sigmatropic shift. So these are the 3 parts which we are going to study in sigmatropic. First we will be discussing about hydrogen shift, okay, in detail. Then we will move to carbon, 1 comma N carbon, and then we will study N comma M sigmatropic shift. Clear? Okay. So, we will start then with 1 comma n hydrogen shift rate. Okay. First we will see the simple reactions, very simple general reactions, then we go in simple reactions like just what I have said now. See, when you write pericyclic reaction, you write both the ways because it can happen, right. So, I number it 1, 2, 3. Just see the electron push because that is okay. Hydrogen. Okay. So, how you represent that? You just write 1 comma 3, you can write hydrogen shift, small h, it also works 1 comma 3 hydrogen shift, or people write 1 comma 3 bracket hydrogen h, okay, way of writing it. Now, it is little bit different from your electrocyclic when you count the pi system, 4n rules and 4n plus 2 rules which you do in electrocyclic. In this case it is little bit different. What you do is that you consider how many electrons are involved in this reaction, that is how you consider. See, 2 pi electrons, okay, as well as 2 sigma electrons. So, you have now 4 electron system, basically this is 4 electron system now, okay. Somewhere you get lost when you go to electrocyclic and this, just you see the pi system. Here you have to see the pi system and your sigma system. So, you see now it is as a 4 electron system. Okay. So, when you apply your Woodward Hoffmann rule, then you apply with this electrons. So, this will be your 1, 2, 3, 4, 5. So, this will be your 1 5 hydrogen shift, and basically it will be 6 electron system. Right, and one more is which we will be discussing. Keep my R here. So, 1, 2, 3, 4, 5, 6, 7. So, it is 1 7 hydrogen shift. So, it is 8 electron system. Right. So, reaction wise now you know how to number it and how to represent this guys and how much electron system it is involved, right. Any doubt on this? Clear. Now, I will bring a small additional point into this reaction. Okay. That is, if I take a system, this is very simple. Okay. If you just remember, if I take a system like this, general representation. Okay. This is your hydrogen. Now, if you know if I heat this reaction, it will happen what 0.5. Okay. But once your hydrogen moves to C and D, it is going to generate a type of chiral carbon. Okay. Then the stereochemistry comes into picture, right. So, it can be two way, one it can be R or it can be S, right. So, if I sorry. Or your C can be like this, okay, nothing. So, this is so you have a C, D, hydrogen and this, okay. Now, in one case if you see your hydrogen, okay, has went to the same phase. Another case if you see the hydrogen as went down, okay, in a opposite phase, right. It has a sort of inversion has been taken place. In one case it has in the same phase. So, that you call as suprafacial, where your hydrogen went in the same phase without disturbing. Another case you call them as an antrafacial. See, slowly bringing a stereochemistry into this shift, that is all. First you know how to do your hydrogen shifts, okay. You know what is 1 3, 1 5, 1 7, how to label them, how to push your electrons, how many electrons are involved. Now, I am bringing one more concept of stereochemistry. If your hydrogen moves without changing the phase, okay, then you say suprafacially. If there is an inversion, then you say antrafacially. Clear? You can visualize this even with orbitals. I will just show how you can see this in orbital way. If I want to draw suprafacial, okay. Okay, so my R and R prime, and this is my hydrogen which I am talking about, okay. This, if you want to think about suprafacial one, okay, how your state should look. So, you R prime, because this has moved like this, so it will be R prime. Okay. Then basically it can revert back giving this. So, this can become now without your hydrogen, can have a system of, yeah, if it is, yeah, it is nice that you R prime, okay. Then you have this one which will be having small, right. So, suprafacially looks to be easy to draw back. Just concentrate on that R and R prime also, okay. That also tells like what phase it goes on. Can you draw now antrafacial? Any idea? I will just give you the picture. Okay, most of the time if this R should be in the, okay, I have an hydrogen here. See, antifacial means your orbital will be in opposite thing. So, now can you think how to draw this? Can you think this way, how the antifacial looks, how these guys can move? So now I want your R, this R and R prime to be, because it has turned like this, right. So your R prime will be on this and your R will be here, right. I just turned this. Now just do, because right. See, I think when you move across, you keep your R and R prime understanding, okay, because that will guide you. And even I have seen people drawing like even if this hydrogen nucleus, this will be big and symmetrical, okay, it does not work like that. Nah? When you have an hydrogen system, you have a smaller lobe across that you have studied it. So, that is how you can visualize your suprafacial and anterofacial, okay, by orbital if you want. So, based on this orbital picture, Woodward and Hoffmann formulated a type of rule, right. Finish. Yeah. This interaction.
It will be within same phase.
This one. See, I want to take this up, na?
No, this line.
Oh, this line you are talking about. One.
That will be within the same phase.
Yeah, it should be in this, because this is connected, na? This is only to say that it is connected. It's an N system. It's not like I am talking about any phase in this line. Yeah, connected. Just a bond system. Not the phase. I am not talking about the phase. That's good. So, what your Woodward-Hoffmann rule says about the system? Type of for 1n system. Okay. If you have a 4n system, I am talking about the electrons. Okay. 4n and 4n plus 2 electrons where you fit in. So, you have heating and you have a photolysis case. Okay. So, 4n system basically on heating gives you anterofacial, okay, and light it should be always it's other way around, suprafacial, and this is suprafacial and this is your anterofacial. Okay. That means what I say is that what is your 1,5? 1,5 is 6 electron system, right. So, 6 electron system will fit in this rule, 4n plus 2. Yeah, then it is suprafacial heating. When it is light, it will be anterofacial. Okay. So, like that you can fit your rules. It exactly works, only one case it does not work, this one, it is your 1,3 shift. There is something you have to learn about your 1,3 hydrogen shift, fine. So what I will do, that exceptional case or that 1,3 hydrogen shift we will see in this class. Okay, I will teach you why it does not fit in. It fits, but you guys know that 1,3 hydrogen shift on heating does not take place. Okay, if you heat, you cannot see, you most of the time you are not observing any 1,3 hydrogen shift. That we will see in this class why it is not happening. Okay, then we will see your 1,3 carbon shift and we will do the problems. Then we will move to your N, ion. Clear? Okay. So, stop the class with this.